So in this problem, we're asked to use the method of joints to find the forces in all members of the truss shown below, and then we have to specify if it's tension or compression. So a good first rule of thumb is to label what points that you want. So we have labeled A, B, C, D, E, F, G, and H. So those are going to be like the points that we're calling like the different forces and stuff. So this will be like FA, FB, stuff like that. And then it's also a good plan of action to go and find any of the angles in this truss that are going to be either repeated or that we're going to need in any of the method of joints equations. So right here we have theta. So this theta is going to be, to solve that, we're going to do tangent -1 of opposite over adjacent. Opposite is going to be 0.6 over adjacent over 1, and that's equal to 31 degrees. And then here we're going to have phi, and that's going to be tangent inverse tangent of 2 over 1, and that's 63.4 degrees. So we're going to need those for our different equations when we're going to do the method of joints. We're going to need those for those different intersections and whatnot. So a good plan of action is to redraw this truss, but make sure that it's drawn in a way that shows us what we're going to need to use, and see if we can find any forces right off the bat. So I'm going to draw. So this, and this here is a 2-force member, so we know that we're not going to have any forces on that right now, so we don't need to draw that yet. We're not going to account for that. So this is our just a rough drawing to just show us what we want to see first. So right here we have this downward force of 6 kilonewtons, and then we also have this downward force. We're going to call that FGN, and then we can call this FGH. Let's call it FGH because it's acting on the member GH. And then we also have forces in the X and the Y directions for A. So we're going to label those as well. And we know that from here to here, so from A to E and F, the member E and F, is 2 meters. And then from the member EF to the member GH is 1 meter. So we're just going to label that. And we're going to try and find FGH and FAX, FAY. So let's write our equilibrium equations. So our net forces in the X direction are going to be equal to 0. And the only force we have in the X direction is FAX. So our force FAX, that's equal to 0. And then from there, we're going to do our net forces in the Y direction, which we have positive force A in the Y direction, minus 6 kilonewtons, minus the force GH, because those are in the downward directions. Downward we're going to treat as negative. And then we can't solve for AY, or we can't solve for the force at A in the Y direction or the force at member GH. So what we're going to do is we're going to do our moment equation at A. So take the moment at A, which is going to be equal to 0. And that is going to be, so this 6 kilonewton is going to create a clockwise rotation, so it's going to be negative 6 kilonewtons times 2 meters, because it's 2 meters away from A right here. Right here is A. And then we're going to have also negative force GH times 3 kilonewtons, or sorry, 3 meters, because that's a total of 3 meters away from A. And from there, we can solve our equations. And when we solve our moment in A, we get FGH is equal to -6 times 2 over 3. And that gives us FGH is equal to -4 kilonewtons. And this is going to be a compressive force because it's negative, so it means that it's pushing down, it's compressing. Okay? And then from there, we're going to plug in our force GH into our equilibrium equation for Y. So from there, we're going to get that our force acting in the Y direction at A is equal to 2 kilonewtons. And that's just an upward reaction force, but it is positive, so that's acting upwards. All right. So now we're going to do the method of joints, and we're going to start at point G. So we're going to draw G. This right here is G. And G has the 4 kilonewtons upward force acting on it, as well as this force of member EG acting, and this force of members FG acting. And then we have this here is theta, and we know that this is equal to 31.0 degrees. So we're going to look at this, and we're going to take equilibrium equations from this point, from the force we see on this point. So net force in the x direction is negative FG, because this is pointing to the left, that's going to be our negative, and then minus our force of EG, but we want the x component of it, so to get the x component of it, we're going to multiply our force EG times cosine of 31.0 degrees. And then we can just draw like a triangle here. This is how we get the cosine. So say this is force EG, and then this is our theta value. So here we have our force in the y direction, and this is force in our x direction. So if it's just some algebra, we're taking into account the triangle, and so the force of EG in the x direction is just going to be equal to the force EG cosine 31 degrees. And then similarly, the force in the y direction is going to be the force of EG times cosine or times sine of 31 degrees. So from there, this is equal to 0, and then we're going to write our forces in the y direction are equal to, this is going to be a positive 4 kilonewtons because it's going upwards, and then it's going to be plus, and this is our force of FEG in the y direction plus FEG sine of 31.0 degrees equals 0. So we take these two equations here, and you can plug them into Wolfram, or you can solve them by hand, and we end up getting force EG is equal to negative 7.77 kilonewtons. And this is a compressive force because it's negative. Negative is going to be our compression. And then we get our force of FG is equal to 6.67 kilonewtons. And this is positive, so this is tension. So these are our two forces that we can solve. We solve to get using point G. So from here, we're going to just continue on. We're going to use, we're going to do point F. And our point F, the forces acting on F are going to be upward force of EF, the force to the left of member F, or member DF, and we have this downward 6 kilonewtons. That was given to us. That was our first thing from our given value from the problem. And then a force to the right, that is our force of member FG. But we know this value. This is going to go there. So these are equal. So we know that this is equal to 6.67 kilonewtons. So from here, we're going to draw we're going to write up our equilibrium equations. So net force is in the x direction. That's going to be our positive F, our positive force with the FG member, which is 6.67 kilonewtons, minus our force of member DF. So minus force F DF, and that's equal to 0. And that's pretty easy. That's easy. We know that force DF is equal to 6.67 kilonewtons, and that's tension. Because it's positive again, it's what we've assumed, and it's positive. So then we're going to do our forces in the y direction, and that's going to be our positive force EF minus 6 kilonewtons equals 0. And there we get force EF is equal to 6 kilonewtons. And that is also tension, because that's positive. So now we have those. So now that we have our forces at F, we're going to move on to point E. So for E, we start there. And then we have this downward 6 kilonewtons. And then we have our force of member CE and force of member DE. And then we have our force at member, that would be member EG. And that's 7.77 kilonewtons. So force EG, which is equal to 7.77 kilonewtons. Okay, so from here, we're going to write up our equilibrium equations. And, so it's important to note that this is the same theta as before. This is also going to be 31.0 degrees. That's like just from our initial analysis of the frame when we took into account the different triangles that were in the system. This is the same triangle that we took the initial angle for. So it's also going to be 31.0 degrees. And same with this side over here. Same theta. So there we know that when we're taking into account the x and y components of these two forces, we're going to be using 31 degrees. So our forces in the x direction, that's going to be negative force CE, because it's going to the left, minus we're going to take the x component of force DE. So that's going to be cosine of 31.0 degrees times force DE. And then we're also going to have the x component of EG. So that's going to be negative 7.77 times cosine of 31.0 degrees. And that's just our x components. If we draw our triangles, force DE, we see that this is theta, so that if we're calculating for x, this is going to be cosine theta, and then y, it's going to be sine theta. And it's going to be the same for both of these triangles. So force DE or force EG. And then from there, this is equal to 0. We can't solve anything yet. We have too many unknowns in this equation. So we're going to go ahead and write our net force in the y direction, which is negative 6 kilonewtons plus 7.77 sine 31.0 degrees. This is the y component for our force EG, and then minus force DE times sine of 31.0 degrees, and that's equal to 0. So from here, we're going to take our two equations. You can plug them into Wolfram, you can solve them by hand, but we end up getting our force DE is equal to negative 3.89 kilonewtons, and that's going to be compression. That's negative, so it's compression. And then force CE is equal to negative 3.33 kilonewtons. And again, that's also compression, that's negative. Okay, so from here, we can move on to our next point. And that's going to be point C. So for point C, we start here, and we have our force member BC, force CD, and we have this force CE, which is equal to 3.33 kilonewtons. And we know it's acting this way. We know it's negative, so that's how we know that it's going to be acting to the left. So it's acting this way. And then same thing here with theta. This is going to be 31.0 degrees. So draw this out, force BC. And then for our x and y components, theta being here, x is going to be cosine, y is going to be sine of theta. Okay, so now we're going to write our equilibrium equations. Our net forces in the x direction are going to be negative 3.33 kilonewtons minus our x component of force BC. So minus force BC times cosine of 31.0 degrees. And that's equal to 0. And from that, we know force BC is equal to negative 3.89 kilonewtons. And that's compression, that's negative. And then we can write our equilibrium equation for the forces in the y direction. Equal to, we have this negative force of CD going downward, and then we also have our y component of BC. So that's also going to be minus force BC times sine of 31.0 degrees. That's equal to 0. And from here we get force CD is equal to 2 kilonewtons. And that's positive, so that's tension. So now that we found point C, we're going to go to our next point, which is point D. So point D is right here, and then we're going to have this force AD this way. We're going to have force BD to the left. We're going to have our force CD, which was 2 kilonewtons. That's going to be acting up because that was positive. That was our tension. And then we have our force of force ED, or I think we called it D before, which was equal to 3.89 kilonewtons. And that was negative, so that's going to be pointed in. That was our compressive force. And then lastly, we have this force DF, which we found to be 6.67 kilonewtons. So we have two different angles this time. So we have this angle of 31.0 degrees, and then we have our other angle that we solved for, which was 63.4 degrees. So when we're going to solve for the x and y components, we're going to be using different angles this time. Instead of like in the last part how we used the same angles, it's going to be different this time. So we can start with our equilibrium equation for forces in the x direction, which is, so we have this negative FBD plus our FDF, so that's plus 6.67, and then we have minus our x component of force DE, so minus 3.89 times cosine of 31.0 degrees, and then we have our x component of force AD, which is going to be negative, so it's going to be minus force AD cosine of 63.4 degrees, and that is going to be equal to 0. So we can't solve for anything yet. We have two unknowns, it's only one equation. So we're going to move on to our forces in the y direction, and that's going to be positive 2. This is pointing up, so positive 2. And then that's going to be the minus the force DE in the y direction, so minus 3.89 sine 31.0. And then same thing with force AD. We're going to take the force AD in the y component, so that's going to be force AD sine 63.4 degrees, and that is equal to 0. So from here, we end up getting, if we plug these into Wolfram or solve them by hand, you end up getting force AD is equal to 0 kilonewtons, and force BD is equal to 3.89 0.33 kilonewtons, and that is tension because it's positive, and it's our assumed sign, so it's tension. So from here, we're going to move on to our last point, which is point B. So now we found our point D forces, we're going to do our point B. And once we find forces here, we're going to have all the things that we want. So we're going to have this downward force, force AB, remember AB. We're going to have this force here at an angle. This is force BC, which was equal to 3.89 kilonewtons. And that was negative. It was our compressive force, so that's why it's going this way. And then we have force BD, which is equal to 3.33 kilonewtons, and that was tension. That was positive, so that's why it's going that way. So we actually only really need our forces in the y for this one, because we just want to find force AB. So we're going to do negative AB, because it's pointing down, minus 3.89, and then this right here again, this is our 31.0 degrees, and we're just going to be solving for the y component. So y component, y, and that's going to be our 3.89 times sine of 31.0 degrees equals 0. And we're going to get force AB is equal to negative 2 kilonewtons. And that's compression, that's negative. It's compressing downwards. So from here, we can rewrite our solution. It's going to be kind of crazy. We have all these different values. So our force AB is equal to 2 kilonewtons compression. Force AD is equal to 0. Force BC was equal to 3.89 kilonewtons compression. Force BD was equal to 3.33 kilonewtons tension. I'll just write a C or a T for tension, so tension. Force CD was equal to 2 kilonewtons tension. Force CE was equal to 3.33 kilonewtons compression. Force DE was equal to 3.89 kilonewtons compression. Force DF was equal to 6.67 kilonewtons tension. And then force EF was equal to 6 kilonewtons tension. And then force EG was equal to 7.77 kilonewtons compression. Force FG is equal to 6.67 kilonewtons tension. And then lastly, force GH was equal to 4 kilonewtons compression. So it's a good plan of action if you have all these like crazy calculations and lots of different work. It's a good idea to just write them out so you can get a better idea of the solution. And then this is what we needed, and we found what we needed for our truss using the joint method.